Very good. So for this last presentation, Ubaid is going to talk about a continuous adjoint solver for variable density flow within XCompact3d. So please, Ubaid. If you are talking, we...
Yeah. Hello. Hey, yeah.
Okay.
Thank you very much. Yes. Thank you very much. Good afternoon, everyone. Thank you again, Sylvan, for inviting me for this workshop. So I'll be presenting work that I've been doing with Paul Bartholomew, who was a postdoc at Imperial, and Sylvan himself on developing an adjoint solver for variable density flows in XCompact3d. And this was meant to be a follow-on to implementation of Low-Mach number capabilities in XCompact3d, and this was funded by the Embedded Computational Science and Engineering scheme by Archer initially. So a quick run through of what I'll be doing here. So I'll briefly talk about why we would be interested in this, what we actually want to do, how we actually do it. So I'll go over quickly the mathematical framework, the numerical implementation in XCompact3d, and then hopefully we'll be able to see it in action, see if it works, and then finally just leave it aside and see what we can do next. So why are we interested in this? So with the increase in computational power, simulations are becoming more and more detailed. Most of these simulations are able to tell us how a system behaves, and we are able to now simulate systems with more complexity, for example, in offshore wind farms, capturing wind wave interaction, turbulence blade interaction, and even fluid structure interaction for floating wind turbines. At the same time, we are able to simulate flows with more physics in them. So, for instance, in simulating pollutant dispersal or aerosol dispersal, we're able to capture effects of humidity, temperature. We're able to consider droplets of larger range of diameters. But fundamentally, one question that sometimes we are not able to answer is how to make a system better. Or, for instance, which parameters in the system, in our model, most affect a desired cost function or something that we want to get out of the simulation. How might we be able to optimize this cost function? How can we make even our model better? So these are all questions that sometimes traditional simulation approach does not always allow us to answer. And for this purpose, I am particularly passionate about using adjoint simulations, because adjoint simulations can provide us with sensitivity gradients in a very efficient manner. So whereas the traditional simulation can tell us how the parameters or the input feeds into an output or cost function, an adjoint model will be able to tell us which parameters, which of those input variables are the most sensitive in affecting this cost function. So we are able to obtain the gradients of the cost function with respect to all the parameters that we might be interested in just one single simulation. So you do not need to repetitively perturb the parameters to find out their effect on a cost function. So the aim of this project is simply to implement an open source continuous adjoint solver for XCompact3d. And the idea is to minimize the amount of changes that we would make to the existing code there, see if we can build it around the existing solver. And that's what I'll show you that we are able to do. So how do we do it? So I'll quickly run over the mathematical framework and then the numerical implementation. So the best way to think about an adjoint problem is to consider a constraint optimization problem. So let's say we are interested in some cost function j, which we either want to minimize or maximize. And this cost function, for example, the drag over an aerofoil, is a function of the state variables, which is the velocity field around the aerofoil, and some input control variables, for example, some parameters defining the shape of the aerofoil. So we define a Lagrangian where the cost function j is constrained by the governing equations, which I write as n, and this covers the Navier-Stokes equations. And you have a Lagrange multiplier there, which is basically the adjoint field. Now, it involves a bit of calculus. So what we do is we know that at optimality, a necessary condition is that the first derivative of a functional is 0. So we take variations of our constraint optimization problem. That gives us the first line over here. It gives us 3 terms, well, 4 terms actually, in terms of variations of the state, variation with respect to the parameters. We set all of them to 0, and by setting it to 0, we obtain an expression for the adjoint equations given in the second line here. And then from this variational approach, we obtain a sensitivity gradient, the gradient of the Lagrangian with respect to the control variables g. So these are the gradients, the sensitivity gradients that we are interested in, dl dg. And this is simply given by these 2 terms here. And you can see that it is directly proportional to the adjoint variable. I'm not sure, can you see when I move my mouse where I'm positioning it?
Yes, we can see exactly what's going on.
Okay, yeah, that's fine. Yeah, so the first term here represents the gradient of the cost functional with respect to the control variables. And the second term represents the indirect effect of the cost functional of the control variables through the constraints with the adjoint variable. So imagine that we have an initial condition. This initial condition defines this initial condition, let's call it G. This initial condition defines how our simulation proceeds, and our simulation is governed by the nonlinear operator n. So once this initial condition affects our flow variables, it will affect our flow variables up to our time t, and that sensitivity is given then by the adjoint variable here. So what I've represented here is just the general framework. It is just a simple optimization problem. We have considered a general functional form M, and what we're interested in this project is to implement it for the Low-Mach number variable density equations. So we rewrite our functional L now in terms of the actual Low-Mach number equations. It gets a bit messy, but the only things to note here, sorry, is yes. So I highlight the continuity equation we have there. We have the momentum conservation. We have conservation of energy. I've kept in a conservation of species. There could be any number of species that we're interested in, and the entire system is constrained by our equation of state. Now comes the algebraic part. What we want to do is we want to now integrate this expression by part. The angle brackets are basically inner products. They're integrals over the entire volume of the domain. So carrying out integration by parts, probably a day or 2 work, and we end up with these equations here on the left side. Okay, I think everyone can see it. I've just kept the actual Low-Mach number equations for reference here on the right side as well, and I'll point out a couple of interesting facts that we get from these adjoint equations. So these are the adjoint equations. These are the equations that I will be implementing in XCompact3d. These are the equations that we will be solving in order to obtain sensitivity gradients. So what points can we note from this? The first point is that we need the forwards variables while we are solving the adjoint. So the way to visualize this is that the adjoint represents a gradient. So effectively, it's a linearization around one point in your simulation. So you need the actual flow variables at that point in order to calculate the gradient or the linearization around it. So that's the first point. If we need the forward solution when solving the adjoint, this means that for unsteady simulations, you need to store the flow variables at every time step. Problem number 1. Problem number 2 is we look at the viscous term in the forward equation. It's going positive. In the adjoint equation, it's negative. What does this mean? This means that the adjoint equations are anti-diffusive, so we have to solve them backwards in time. That is the second point that comes out. Third point that comes out is that the adjoint equations are forced by derivatives of our cost function. So although the adjoint equations will always be the same, we can choose to optimize different cost functions, and the way these cost functions influence the adjoint field is through these forcing terms. The derivative of the cost function with respect to the velocity will force the momentum equation, and so on and so forth. So in this way, we have developed three ideas that the adjoint equations will have. We will have to store the forward variables before we solve the adjoint equations. We will have to solve the adjoint equations backwards in time. And finally, we can have forcing terms in our adjoint equations to obtain specific sensitivities. So the way we implemented this numerically is in the XCompact3d code. The entire framework, everyone is well aware of it, so I won't go into detail. I'll only say that the idea why we chose a continuous adjoint and not a discrete adjoint, this is something some people might be familiar with, is that this would involve minimal changes to the existing code. The idea was to use all the existing infrastructure that has already been written to solve just a slightly different set of equations. So it's almost the same fractional step pressure projection algorithm. The only difference that we make is that we pass a flag to the same old subroutines saying whether we're going forward direction or the adjoint direction, and that just changes a sign here and there. Okay, so much of the architecture is exactly the same as it is for XCompact3d, the Low-Mach number solver. And the only additional thing that I've added is there's an additional module similar to the boundary condition module that already exists, but we now call this the adjoint module, where you can specify what cost function you want to optimize for and manually enter the derivatives and forcing terms. So that's just one file that a user would have to edit, add in what cost function they're looking to optimize, add in the initial conditions, and that would be the only change needed. At the same time, I've written a module with all the adjoint equations in it, and that can be just used repetitively. So does it work? So we implemented this. Now, the most important thing for an adjoint solver is to check that it actually works. So the case that we'll be using is a temporally evolving planar mixing layer at a Reynolds number of arbitrarily defined as 400. So the mean field is just a standard Tanch profile. We allow for variable density effects by including a mean density gradient. And we superpose some divergence-free perturbations on top of this mean flow. This is the initial condition. The initial condition is therefore the mean field, which is the Tanch mixing layer, plus these plus this defined perturbation of amplitude A. Now, in order to check that our adjoint solver works, we select a cost function defined as the perturbation kinetic energy. So at a certain time, we simulate the mixing layer forward from this initial condition. And at that final time, whatever T1, we measure the kinetic energy of the perturbation compared to the mean flow. And this is our cost function. And the control variables in our case, we want to find the gradients with respect to the amplitude A. This is how we will test to see if our gradients are coming out correct. So what that does is that means that the initial conditions for the adjoint, when we are simulating backwards in time, are simply given by the expression, the perturbation velocity field itself. And the adjoint field, the gradient that we're interested in, is dj cost function with respect to A. And this is simply given then by the inner product between the adjoint velocity field at time t is equal to 0 and the initial perturbation field. And this gives us the adjoint gradient of interest. And this is what we would use to verify that our gradients are coming out correctly. So how do we actually verify it? So we go back to basics of Taylor series. We know that a finite difference gradient expression would simply be given by the cost function for a slightly perturbed amplitude minus the cost function for the original amplitude divided by the perturbation. The Taylor series expansion gives us that we can write the cost function at the perturbed value in terms of the gradient and the original cost function. Using this, we can then derive the adjoint error. Theoretically speaking, the adjoint error, if we just rearrange the expression in the second line, should converge at first order. And this expression epsilon, when we subtract it from 1, will give us the error in the adjoint gradient. Another check is the second order Taylor remainder, which if we again rearrange the expression in the second line, we can see that this expression here should have second order convergence if our gradient from the adjoint is correct. So these are the two things that we will use to check if our adjoint gradient is correct or not. So what do we find? So we'll consider a mixing layer at a Reynolds number of 400. We will consider both a uniform density case and a variable density case. And the variable density case will be corresponding to a density ratio of 2 between the two sides of the mixing layer. And this is what we find for now. Yeah. So the solid line represents the uniform density case, and the other lines represent the cases with variable either temperature or variable composition. So what we see is epsilon on the x-axis corresponds to the magnitude of the perturbation in the finite difference scheme. We find that the uniform density case shows extremely good convergence properties for the adjoint gradient as we take smaller and smaller perturbations compared to the finite difference scheme, even going up to 10 to the minus 5 or 10 to the minus 6. For reference, a discrete adjoint solver should be able to give it correct to 10 to the minus 8. Half of machine precision is the golden standard that an automatically differentiated discrete adjoint solver will be able to give. That's the best that you can get, is a perfect convergence with double precision up to 10 to the minus 8. So with a continuous adjoint solver, getting it up to 10 to the minus 5 or 6 is been seen in previous studies. So it's not exactly bad news. And the error in the gradient shown in the right-hand plane can be less than 0.5%, less than 0.1%, 0.02%. So we are very happy with the uniform density solver. The interesting point comes when we are looking at the variable temperature or composition cases. We see that the adjoint gradient tends to level off. So the best we can get is an order 1% error, which is not exactly bad news, because a non-uniform density case, we have a lot more nonlinearity in the expression. So you have a rho u term in the momentum equation and so on and so forth. And it has been seen in other studies with continuous adjoints that finite difference calculations for the gradient tend to suffer from irregular behavior after a certain point due to round-off errors in finite difference schemes. So I am not concerned that this is just within the realm of what we expect. The continuous adjoint solver will only give the exact gradient as the mesh resolution approaches infinity. So this is all part and parcel of the errors in the discretization between the forward equations and the adjoint equations. Combine that with the fact that, yes, in the Low-Mach number case, it is a bit more ill-posed. So we expect this. I have seen this before when calculating adjoints with Low-Mach number flows. The solver is a bit more sensitive. So on the whole, my conclusion so far is it does work. Our gradients are correct to within a couple of percent. So that's just what it is. So what do we find? Can we now use this gradient for something a bit more interesting? So let's go back to our mixing layer case. And whereas while we were carrying out the validation, we had imposed a particular form for U prime. Now we will say, let's just find U prime. So our optimization condition is what initial condition for U prime maximizes some measure of mixing in this mixing layer. What that means is we now have to come up with some cost function which measures mixing. And we have two cost functions in mind. More could be made up. The first cost function is, again, the perturbation kinetic energy. So one theory could be that any initial condition that maximizes the perturbation kinetic energy, it means that there will be more mixing in the flow. This is just a theory. We'll see whether it works well or not. The idea here is that Kelvin-Helmholtz instabilities naturally arise in a mixing layer. So if we were to excite the Kelvin-Helmholtz instability, that might be the best way to mix the mixing layer. Okay, that's one theory. The other cost function we could use is the actual variance of the scalar fields. Now, this isn't a passive scalar. Y1 is not a passive scalar. It's a species field. So it's the measure of the concentration of one species. They have a density field associated with them. And we'll consider one species, the mixing between between two species which have a density ratio of 2. So one is twice as dense as the other. So these are going to be our two cost functions. And what we're going to do is now use the adjoint gradients that we calculated, fix it within a steepest descent or a conjugate gradient algorithm, and see what we get. What kind of structures and initial conditions do we get? So what do we find? First of all, let's consider the case with maximum perturbation kinetic energy. So this is what we get. So when we are maximizing, our objective here is to maximize the perturbation kinetic energy. The optimization algorithm, which utilizes the adjoint gradient, tells us that the initial conditions, the perturbation fields shown here on the left side, which maximize the perturbation kinetic energy, are first of all inclined against the mean shear. This is exactly what we expect because a OR mechanism tends to maximize transient energy growth. And the final condition, which is showing the scalar distribution across the mixing layer, shows that we are exciting what we would call Kelvin-Helmholtz kind of structures. Okay, so this is what maximizing perturbation kinetic energy is doing. Now, what happens when we try to minimize the variance, which technically is a better measure of mixing, and this is what we get now. So when we try to minimize the variance for the same time, for the same flow, the initial condition now again is inclined against the mean shear. So again, it's an OR type mechanism, but now the wavelength is much smaller. So we are looking at a much higher wave number initial condition. And what is it doing? It is exciting the layer between the two species. It's pulling and contracting it here and there. It's creating a large surface area across which material can diffuse across the mixing layer. So fundamentally, what we're seeing is two very different outcomes coming out of our adjoint based optimization algorithm, depending on whether we want to maximize the perturbation kinetic energy or we want to minimize the variance. And the minimizing the variance is actually a better way of mixing this. Depends on more philosophically what you understand by mixing. If you want the mean variance to reduce in a flow, this is what you would actually want. So I think this is what we find so far, and this is just showing the solver in action. I don't know how much time do I have left, Sylvan?
You are way over your time limit.
Okay, then I'm done. Yeah. All right then. Okay, yeah. So this is basically what we've come up with. It's a highly efficient solver for obtaining sensitivities. It's naturally applicable to studying transition or nonlinear stability. Yeah, I'll be happy to. I thought I might show some examples of how this has been implemented in the code, but we don't have time. That's fine. I'll be happy to take any questions. Thank you.
Thank you very much. Thank you, Ubaid. That's very interesting, and I know for a fact that there's a lot of people have been trying to play around with iJoint solver within Compact3d or XCompact3d, but this one is targeted to the Low-Mach number equations. So one question is, what will be the boundary conditions for the adjoint equations if a convective outflow boundary condition is used for the forward problem?
So that is standard for the continuous adjoint. You just have to derive it. I mean, like you have to go through the derivation, and it comes out as some kind of yeah. So for the convective outflow, I believe you will get a Dirichlet condition for the pressure, which is not exactly compatible with how the pressure solver at the moment is in XCompact3d. it shouldn't produce a large error in the gradient, because from my own experience of using this, even using an equivalent convective condition for the adjoint boundary condition, you will get a small error, but not a large error. Overall, it will still work. The formally accurate boundary condition for the adjoint will involve a Dirichlet condition for the pressure. That I can pretty much say. Yeah. But you can derive this out from the equations while you do the integration by parts. It comes out.
Great. Thank you very much.
All right.